Hello, everyone. Thank you for coming. So before we start, we have two announcements. Actually, one announcement. It's about the conference that we are planning to have on July 24th, 25th. This is going to be PyData, PyCon conference, meaning that it's both about data science and about usage of Python in general. Now, this is going to be a community event, meaning that if you have any idea of presentation, you have done anything interesting in your work and you want to present, please be free to submit the proposal. The call for proposal will be announced in like a week or so, right? So it doesn't need to be a scientific research paper or whatever, just like anything interesting that you have done and you'd like to talk about it. So the PyData PyCon will be July 24th, 25th. And the second thing that I would like to say is that the research that Davit Ghazaryan will talk about was funded by the Afeyan Foundation. It was a research grant that was done and given to the research group last year, right? And we finished it this year, and there are a few papers that are in the pipeline that are coming to be published by this, funded by this grant. Now, thank you. And the last thing, if you have any questions, please keep them to the end of the lecture, okay, end of the presentation. Thank you.
So, thank you, Habet. Hi, everyone. Thanks for coming. And I'm Davit Ghazaryan. I'm an Adjunct Lecturer at American University of Armenia. And first of all, I want to thank to the organizers for inviting me for this talk. So today we'll talk about the PID controllers. So PID controllers are almost everywhere. We can see them in almost every industry. We are using that PID controllers to control the UAVs, drones, in robotics, in industrial systems, almost everywhere where we need that something related to the stabilization. And despite the rise of the modern control theories, despite this, their rise, PID controllers remain still the dominant in industry because they are cheap, they are easy to implement, easy to maintain. But they have one main persistent drawback, that coefficient tuning or gain tuning problem. Usually we are using every stick or manual tuning methods. And today we'll represent that reinforcement learning approach to adjust or to learn that reinforcement, that PID coefficients. So the outline of today's talk will be, we'll have some motivation why we need reinforcement learning. Then we'll discuss the main concept of reinforcement learning. Then we'll have some refresher on basic control system loops, mainly this closed loop feedback system where actually PID controllers are applied. Then we'll discuss actually what are this PID, what these terms proportional, integral, and derivative components mean, and we'll discuss in detail the main limitation of that classical PID tuning methods, and then I will introduce reinforcement learning as a tool for solving, for addressing that problems. In the end, I'll represent also that RLDroneSim platform, which was the result of that research grant founded by Afeyan Foundation, Family Foundation, and we'll discuss some future improvements for that platform. So the stability in the control system is one of the main task, and we need to have a very good tuned gains in the PID controllers, and sometimes that when we are tuning that your PID gains in some environment, then if the environment is changing out, you are applying that learned gains in other domain where environment has changed or some conditions were changed, then your controller will not behave as it expected. So here we have three different controller behavior. So this is so let's say we have some stabilization task. Our task is to keep the room temperature in that 22 degrees, for example. So this is that set point, and three different controllers are solving the same problem. Here we have that very stable but very slow controller. It is reaching to this point very late. So on the other hand, we have extreme. We have this controller which is reaching very fast to that set point, but as the speed is very high here, then it is overshooting here, and it needs to come back here. And the well-tuned version is this bold one. And we want to that our controller adjusted PID our controller with adjusted PID controller behave like this. So reinforcement learning will be main tool for solving to address that limitation for that PID gain tuning. So let's discuss that main concepts of the reinforcement learning. So this is the main loop of that reinforcement learning. So you will see this loop in almost every reinforcement learning literature. So we have our agent and environment. So all of the main components are represented here. So this is our agent. This is the abstract term. This can be anything in our terms. In our context, it will be our controller. But this can be the, let's say, bot, which is doing that automated stock trading. This can be the piece of software which is driving autonomous car. This is just the abstracted way to say agent. So, but this is the at the end. This is that our piece of software that will do that learning process. So this environment is everything which is outside of our environment, and usually it's out of control. And we have this state, reward, and action. So here the key characteristic of this reinforcement learning is that there is no supervisor here. If we do that comparison with the supervised learning pillar for that machine learning, maybe you have seen that picture: supervised learning, unsupervised learning, and reinforcement learning. So this distinction was that based on the data. For the case of the supervised learning, usually we have that collected data set, and we have the labels. And when we can, by having that through labels, we can compare the output of our models, and it will say that prediction was true or not. Let's say we are doing that classification task. Here we don't have any data set in reinforcement learning setup. We'll get that data during that learning process. All of this reinforcement learning is about that sequential decision making. And here we have this discrete time step, and we have this sequential data stream, and here we don't have this IID, which is the main assumption in that supervised learning concept, where we are assuming that our data was generated identically and from the identical, and they are generated independently. So here, actually, the data that will be generated is the agent's action. The agent's action are actually affecting what data will be generated later. So what is happening in this loop? So from the agent's point of view, agent is at every time step is receiving this information about the state and reward. So this state it is usually vector. It can have multiple components, and the reward usually always is one scalar, and all of the goals that we are trying to solve. There is this theorem of reward hypothesis, meaning that all of the goals can be reduced to this one scalar matrix, and the goal of reinforcement learning is in the future is to make this kind of actions which will maximize the future reward, not just the immediate reward after just one action, but the sum of all of that future rewards. So this is every time agent is receiving this ST and RT, and it's picking action based on that information that it has. And from the points of environment, at each time point, environment is receiving this action from the agent, and emits some that observation or the state information, and this reward. So sometimes this reward is a part of the environment, but that can be the cases when we need to construct our own reward function. Let's say if our agent is playing some game, a computer game, and the goal is to get a maximum point. In that case, that maximum point, the point is shown in the screen. So in this case, that score or reward part can be constructed from the environment. But in our case, this UAV PID coefficient tuning, we need to construct our own reward function, and this is very important component, and this is actually the challenging part of the reinforcement learning when we are applying that reinforcement learning in other domains. You need to come with your very well designed and shaped reward function, because this is actually shaping what your agent will learn. So here, and this loop continues, and during this process in this loop, agent is trying to learn what actions to take, which is leading to the higher rewards. So we are usually this all reinforcement learning concepts are modeled in this within this framework of called the MDP, Markov decision processes, meaning that here we will have this total of five components: state, a set of all of possible states, set of all of the possible actions, state transition matrix, reward function, and this gamma, which is that discount factor. And by this state transition, this set of state and set of the actions, this can be the discrete or continuous. And actually, there are the algorithms which are solving the reinforcement learning algorithm, which are addressing this reinforcement learning, are completely different. If you are operating in that finite state and finite action space, if you are operating in the finite infinite number of state, but still the actions are finite number, then so this is another family of the algorithms. And in the case of the number of states and number of actions we can take any numbers from any interval. In that case, we are applying this deep learning concept. So here the term of deep reinforcement learning, we are applying deep learning as a function approximator, and it will try to do the very good estimation of this when we are entering this state and action, and it will give us the value of that state values. So what is here we have the Markov decision process, and what is this Markov property? This is the property of the state, meaning that so this definition was given by the Markov, and this is said that if we are in some state, and we have included all of the relevant information in that state variable, meaning that we can throw away the history if that current state contains all of that relevant information. So to give you the example, let's say our agent is controlling some drone, some robot which is trying to find the exit from this state. So we have this something discrete. So this is the finite set of the states, and we have the finite set of the actions, left, right, forward, and backward. And in this case, if in the state information we are keeping the information about the current state and the velocity and the direction, these three information will be enough to identify what will happen next. If we are, let's say we are not including the information about the current state, then we'll know this information at some point. We know that our drone is moving with this speed, with this direction, but we can't estimate where it will end up. So this the second one will not have that Markov property. But if we are including that also the information about the current state, then that our state variable will be Markov. So this is actually giving us the opportunity to throw the previous throw away the history, and the control actions can be started from that. If you are at that moment, it doesn't depend what happened before, and we can continue our control. So another example. Let's say this is some current situation in the chess game. So let's say two players were playing this game, and here we have this situation, and at this moment we can take away these two players, and two other players can come here and continue playing. It doesn't matter how they get to this position, who has taken the queen or the bishop. The queen that bishop was taken 10 moves ago or 15 moves ago. It doesn't depend. They can continue from here. So this, again, we are including all of the information. If you let's say take cover some part of here, then in that case this will not have the full information, and it will not have the Markov property. So the goal of the reinforcement learning agent is to maximize this so-called return, which is the sum of the future reward. This is the reward that our agent, let's say we are starting from some state, and from that state we are after first action we are getting this immediate reward. After the second action, after that loop is continuing, and environment is giving us another information about the new state and the reward. This comes from the environment or the reward function that we have shaped for ourselves, and then here we have this discounted factor here, that we are not giving the same importance for all of the future rewards. If we'll take the gamma as 1, then we'll have that meaning that we are giving the same importance for the reward in the next step and the reward after the, let's say, 10 steps. And here we can have also this distinction between episodic tasks and a continuous task. Episodic tasks are the tasks which have natural end. Let's say that in that example, that our robot needs to exit find the door. Then it will do first in the beginning. It will do some random exploration, and finally, if it will find that exit door, then our episode will end, and we'll start a new episode, and this learning process will continue. But let's say if you are applying in some problem where there is no end, let's say our reinforcement learning algorithm is trying to control the city traffic, control that traffic lights, and in this case, this is not this process doesn't have any end. This will do in the infinite loop. Of course, there's some disaster can happen, and then everything will be ended. But in the terms of the reinforcement learning, this is the continuing task. So the goal of our agent is to try to find its best action, which is not maximizing just the immediate reward, but the sum of all of these future rewards. So in our now let's formulate our reinforcement learning problem for adaptive PID tuning. So our agent here will be some reinforcement learning algorithm. In our case, we have taken this TD3 algorithm. But there are also other algorithms, and our reinforcement learning agent should learn how to adjust these PID coefficients. So the environment here will have some simulation mode. We should have that autopilot. We are using ArduPilot's SITL, system in the loop simulator, and for adding some physics, we are using this Gazebo, and these three will be I will show how we have integrated all of these three components. So in the state variable, we have included this. We can include this that tracking error. So this will be task dependent. If you are solving that, let's say we want to keep the drone in this position, then the state variables can be different. And actions here are to adjust this KP, KI, and KD. So this is that. Gains or coefficients of that PID controller. We'll discuss that PID part later. And the reward, in the reward, we should penalize that error we should also have the term in our reward function which will penalize that high oscillations, or also penalize that aggressive control, because usually we have some physical limitations in our control environment. So one of the versions of that reward function can be this one. So this alpha, beta, and this lambda are just hyperparameters. We need to play with these hyperparameters, and the goal of our agent will be. So those are the errors, and that this in this minus, this alpha, beta, and gammas are positive numbers, and it will try to. It will find the maximum. If it will maximize this reward function, then it will keep this error rate and this UT as small as possible. But we can have another modifications also, or another reward function. And again, this is very important part for this reinforcement learning task. What your agent will learn to maximize your the reward function. Maybe in your reward function you are intending that your reward function should do this one, but actually from the mathematical point of view it can do completely different thing. So now let's try to change the focus from reinforcement learning to the control system. So we have defined what are this reinforcement learning agent, environment, and state action rewards here, and here. But what we are actually controlling, we are controlling that PID gains or coefficients of that PID controllers. And now let's discuss what are that PID controller actually look like. So this is that justification why the PID controllers are still in use. And reinforcement learning here is not to replace that autopilot or controller. Here we are using reinforcement learning for adjusting or enhancing our controller. So now let's discuss this open loop and closed loop system. So this is that open loop control system. So we have here some input. Again, we are controlling the room temperature at 22 degrees, let's say. We are setting that 22 degrees here. And in our controller, let's say we have 5 heaters here, and then we are programming based on our knowledge about the room and the outside environment. That let's say switch this in the maximum power. Let's switch this in the half power, and after sometimes switch off this one and switch this one. So we can program this, and hope that at the end it will produce that 22 degrees and will stay at that 22 degrees. But in real life scenarios, when your system is not isolated, there are external factors. So in this case, of course, the outside temperature will affect your room temperature, meaning that we need this closed loop. Meaning that we should send this actual, let's say that our desired temperature is 22 degrees, but our output is 20 or 25. We need to send that information back here and make adjustments. So this is how that closed loop feedback system is working. So so feedback is very important. So this is negative closed loop feedback system with negative feedback, because we are subtracting this error, this output variable from our desired or set point. And after that, we can generate our new control signal based on this error time. So this is if this is higher. Let's say the 22 and our actual output is 25. We have that positive error, meaning that our controller should generate some control signals which will switch off that heaters. If it is less than this one, then we need to increase the power. And we need to somehow convert this error signal into the control signal, and which will this is the job of the controller. This is not the task of the reinforcement learning agent. So this is the job of the actual controller. And what is the good controller and bad controller? So here we have some metrics. So this is that overshoot. So this is our set point. So this overshoot is showing that the maximum overshoot. So this is the 25, and let's say our maximum overshoot is 30. And in some cases, maybe we don't want to have this kind of overshoot. For example, let's say we are experimenting with some drone here and asking the drone to take off from here and keep the position at the 2.8 meters, and the height of our room is 3 meters. And if that overshoot will be let's say 3.2, then it will hit to the ceiling, and we'll have that so we'll have the damage our control system. So this is very important parameter. Another important parameter is also this settling time. How when our control system will reach to this interval. So this is then set point plus minus some delta. When this is acceptable from engineering point of view. Of course, it will not still stay in that 22 degrees. We'll have some 22.1, 21.9. But if that interval is acceptable, this is that settling time. Another component is this rise time. When our controller or our system reaches to that set point. If you have another controller which is reaching to that set point, this one, maybe we'll prefer this controller. This all are task dependent. We need to fast, accurate, and stable controller. And the basic idea how we can convert that error information about the error to the control signal. We can take this error, which is the difference between our set point and that actual output, and multiply with some k, and this is the kind of the scaling factor. And usually here we have also some converters which are converting. Let's say that error is in the difference of that temperature, and it is converting to another measurement unit, or converting it to the voltages, which can be later applied to our actual plant, which is the object that we are controlling. So, and this is that proportional controller. So this is that first term of that PID. So this is proportional controller, meaning that we are reacting on the current error here. So, and this is that scaling factor, and this is a hyperparameter, and there is no science, or there is no any paper which will say that for that specific task take this KP as 1.10 or minus 5. So this you should try this so this is that manual tuning part. If you choose larger KP, then it will have that race time will be very fast. But if you set this too large, then maybe we'll have that oscillation or even instability. So it is very important for this PID in this P controller to choose proper. So usually this is not just 5.65. Maybe you will have some range which is acceptable for your task. So this is reacting on only the current error. So this is trying to reduce to this error, but if we want to keep our control signal can't be actually zero. This means that from this equation, so we can derive that if this is not zero, we can't remove our control action completely. Let's say again, this is our drone, and if you switch off all of the control actions, then it will mean that the gravity still exists, and it will fall, and then we need to switch on again our control signals, meaning that for this PID, for this P controller, if we are using only this P component, we'll have this steady state error, and this P controller can't eliminate this error. So that's why we are introducing this memory term, this integral component. So this is the accumulates from that all of the previous errors, and if that steady state error still exists, it is forcing the controller to generate that control signals, which will try to eliminate this steady state error. But so this integral component is actually solving the problem of that steady state error, but it causes another error. In some cases, it can also, if that remaining error is that accumulated error is large, then it will cause larger control signals, and we'll have that overshooting, or we can have oscillation, or our system can become unstable. So we need another term to penalize also this term. So here we have that derivative component. We are adding that integral derivative of the error. This is kind of responsible for measuring the speed of change of the error, and if it is predicting that the error is changing rapidly. It is playing the role of this damping. It has a damping term, meaning that it will try to reduce that control signal. So all of these three components are compensating the negative part of each one. And if we sum up, so this proportional component, this P component, reacts to the present. What is happening right now? What is our current error? This in the integral part reacts what has happened to in the past, and that this derivative term is trying to predict what will happen in the future and reduce that control signal, which may cause that oscillation or overshooting. So hence here we have this PID. So this is that PID controller. So we can have also PD controller when we are just taking into account the P and D component or PI component. These are the behaviors of that various controllers. But this is that for specific P and the coefficient of P and D. Maybe we can, let's say, for this PD controller, we can find the one which is better than this PI. So, but the best one between all of these possible P and PD, PI combination is this PID, which is fast and accurate and more stable. Because always from this PID we can get, let's say, this PD. If we set that gain coefficient in front of that integral component to 0, we'll get that PD. If our agent or during our tuning process, we'll find out that we don't need that integral component, then that PID will become just a PD controller. So this is that. Now this is our closed loop control system. This is our controller with all of these components. So PID component, and now let's discuss how to choose. So we said that this is the fast, stable, accurate model. But all of this, the performance of our controller depends on this well-tuned gains, this KP, KI, and KD. And so how we can solve this? So this PID tuning is really from the in real life. This is a very challenging task because again all of the performance depends on how you are choosing this KP, KI, and KD, and there is no universal methods that for that specific task. If you choose this, or some proportion of this, then your system will be stable and you will have that fast, accurate controller. You need to do this trial and errors. So how we can choose these gains, the natural question. So this is that computation, the real problems of this. Let's say one way of tuning that gains are this manual tuning. This is the trial and error. You are choosing some components from some interval, and then increasing this one, decreasing this one. So actually we have infinite number of combination here, and also we need maybe there's some intuition, the background or experience of the engineer, and also that knowledge about the domain where that your controller is you are applying your controller. So this Ziegler-Nichols method is another method for this PID gain tuning. So you are increasing. So if you are starting from small kp, this proportional part, you will have this exponential increment of your output variable. And if at some point you are increasing that your kp and it is causing that oscillation, then you are stopping and you using that value of the k. Another approaches can be this model-based tuning, but all of these are again for problem and environment, and domain specific, and you need to. There is no universal way. Maybe for someone that manual tuning will work. Let's say during the pilot is driving that UAV. And seeing that something is wrong with from that current conditions, and then asking or changing that some KP, KI, or KD, and it will now we have another controller and trying to drive that UAV, and but this is that very risky, because if you make the changes which will cause that oscillation or instability, maybe your drone will fall down and you will lose your drone. So this is very risky to do this PID tuning in the real life and real time environment. So this is time consuming, the limitation of this classical PID tuning methods. This is the time consuming, environment dependent. And also if there is some change, let's say your drone is delivering something and it is dropping that, and that let's say a load was 1 kilogram, and this is very large amount if you are comparing with the weight of your drone. And after that, all of the dynamics of your UAV will be changed, and maybe your controller, if your controller will not react immediately, you'll get into that instability mode again. Your drone maybe will be down. So static gains, the core problem here that we have these static gains, but the environment can be changed. So now the question is, can we automatize this problem? Yes, and here we can have these two scenarios. We can use reinforcement learning to again learn some static gains in some simulation mode. Let's say we are doing that lots of experiments, playing with lots of parameters with KP, KI, and KD, and finding some set of that KP, KI, and KD. And this is the best way, which is working well for almost well for all of the possible scenarios. But another approach can be that we can do this adaptive control, meaning that our that KP, KI, and KD will be changed according to the environment change. So this is that adaptive control, and now we'll apply reinforcement learning for this adaptive control. So instead of manually tuning the gain, we'll turn this manual tuning into the learning problem here, and our reinforcement learning agent will play with this KP, KI, and KD gains. We are not so we can apply reinforcement learning directly to that motor voltages and trying to control that RPMs of the motors, but we are abstracting one layer up, and we are dealing here with this gains of the PID coefficient. So we'll use actual autopilot in UAV or any PID controller. We are just playing with this coefficients. So now again, our reinforcement learning formulation. This is our agent. And our environment, we should include this UAV, all information about our UAV dynamics here in the environment. We should have the real autopilot controller here, and we should also take into account that external disturbances. And the state, we should include all of the relevant information in this the state to make it Markov or close to the Markovian. is our action, and this is our reward function. And here the simulation part is very important for when we are applying reinforcement learning for solving some problem, because that exploration reinforcement learning agent will need more exploration. It should try a very various combination of that actions, and maybe that action will harm or crash your UAV, or your damage your control system, or maybe there are some safety issues. You can't operate directly with that control system. That's why we need for reinforcement learning, we need some simulation environment, and this will be in that environment. And in that environment, our drone or our controller can try all of the possible action, do the exploration, and after that learn the best actions, which will lead that best reward in the future. The possible problem here is this sim to real gap. This is very well known problem in reinforcement learning. And you have that simulation environment, and in that simulation environment, you are calculating something. Your agent is learning inside this loop, but actually that real dynamics in your environment, in your simulation environment, and real life are very, very different. And your action in this environment is taking your agent from here to here, but in real environment, your action from here to here can have other completely different consequences. So this is very important to have a realistic control simulation environment. So for that simulation environment, we have chosen this gymnasium environment. This is very well known platform for reinforcement learning experiments. So there are lots of environments for basic toy examples. That there is some toy robot. It is you are trying to teach that robot to walk, to run, to hit the ball. But this is also that has this standardized API. And you can create your own custom environment there. So that in that standard environment, you should have this reset function. This is every time after your episode is terminating, we are resetting that environment. And this step action is returning these 4 values: observation, reward, done, and info. So this observation is that in that environment loop, it is returning that action in this step action, we are giving this action, and this that gymnasium environment is returning this observation. This is the information about the next state, the reward, how good or how bad was that action, and this done is keeping that information about that your episode was terminated, or you have reached to that terminal state, because in continuous task we usually have that maximum number of episodes. Let's say one maximum number of steps, 1 million steps, and if after 1 million steps our agent is not reaching to the terminal state or the goal, we are ending or truncating our environment. Our episode will start. We'll do another reset, and that episode will start. So there is high level frameworks for all of these modern reinforcement learning algorithms. One of them is this stable baseline, and in this stable baseline, all of the modern reinforcement learning algorithms are implemented there. This is very similar that when we are using that, let's say TensorFlow or PyTorch for deep learning tasks, we are not implementing that from the scratch. We are using that TensorFlow and PyTorch, and we are constructing our architecture of neural network, and it will do that automated calculation, all of that gradient, etc. And here this is very high level of framework, and we are just this TD3 algorithm. TD3 algorithm is implemented. The TTPG and other algorithms are implemented, and you can just use, and these two are can connect these two they are very friendly with each other, and you can connect this stable baseline with this gymnasium API. So we need that simulation environment. We are using this ArduPilot Software-In-The-Loop simulation environment. So this is real. So this ArduPilot has its own controller, which which they are using for real UAV flights. So it is a software in the loop. So here in this software in the loop, instead of the real hardware, this is some piece of the software, but all of the dynamics is the same. So the control logic is exactly the same, which is in that real UAV. And with this gymnasium environment, the connection is done using this Mavlink protocol. And this SITL, we are using this SITL as an environment, but this also to make this realistic. So this is that SITL. So let's say this is that map, and this is that. Here we have some mission. The drone should go from here, and come back to this state, the same state, or other state. So this is how this soft SITL look. All of the information that related to that control that flight are available here, and we can have access using the Python to all of that variables. To add, to make it more realistic, we have added this Gazebo physics engine. Again, this is works very well with this SITL, and this is making more realistic our simulation environment. There are lots of other physics engine. We have chosen Gazebo, but later we are planning to use also other physics engine to make our simulation environment much more realistic. So all of the aerodynamics are the same. It is giving us the information about this IMU, inertial measurement unit, information about the gyroscopes, information about the GPS, information about that all of the acceleration with all of these axis, and this will give us that very well suited simulation environment, and this gives us the hope that we'll have that sim to real transfer will be we'll have that very well simulation, and the actions that we have learned in the simulation mode will be also have very good consequences in that real environment. So this is our RLDroneSim. During that project, we have designed and constructed this RLDroneSim environment. So this is again sponsored by Afeyan research grant, and this is open source platform. All of the codes are available via this GitHub link. Also, we have this documentation here. So these are I think this will be shared with you. So these are the active links. You can click, and we will have all of the codes available here. So in this RLDroneSim, we have combined all of this ArduPilot SITL, Gazebo, and that stable baseline. And the main architecture is this one. So this is our RL agent. It is taking that agent. It is playing with that KP, Ki, and Kd with these gains, and it is trying to adjust them. There are two approaches. Which one to apply? One is when we are giving some range for let's say we are giving some range from this KP from -100 to +100, and it will take some random values from that environment, and for the same then another interval for Ki and Kd. But another approach is when we are starting from some point and trying to adjust it, adding some plus or minus from that starting point. So in our example, we have chosen this approach, and then it is sending that information to this gymnasium environment. Then it is communicating with this ArduPilot SITL via this Mavlink protocol, and this is our controller. In this, it is sending control commands to the Gazebo physics engine, and it is returning that sensor data, all of that sensor data, and based on that, this gymnasium environment is returning this reward and observation to our agent, and so this is that loop, and in our reinforcement learning lives in this loop, and it is trying all of these actions, and at the end it will learn that how that best best combination of of this P, Ki, and Kd. So that will be the case when we are going in the direction when we want to choose that learn some that static gains. But as we have chosen going to the direction of that adaptive control, in this case we'll implement this that learned weight in this logic. So this TD3 algorithm. So inside this TD3 algorithm, there are lots of neural networks which are doing this during that learning process. They are adjusting their weights, and then later we can implement this TD3 in some small computational device, for example, Raspberry Pi or NVIDIA Jetson, and then it will send that our current state information to that Raspberry Pi, and then it will send that the best values of this KP, Ki, and Kd for the specific case, and then our drone, our UAV will respond to the environmental changes. So this is our training pipeline. I have already described this. So here our final RL problem for using the RLDroneSim platform. So these ones are, so we have these nine components in the state. So this is we are including the position deviation. So let's say the task. This is for the task of we are keeping. We are keeping the drone fixed in this position. This is that hovering task, and here we have this error. This error across the x and y plane, and that altitude deviation. And we have these 3 velocity components and 4 acceleration components. Those components are from the actual controller from that ArduPilot SITL. So there they are using that some cascaded PID controller. So this is our reward. We were playing various combination of reward function. At this moment, we are choosing our reward function is this one. So we are subtracting from 100 this 9 normalized sum of all of these normalized components. So we are normalizing these errors between this 0 and 10 interval, and if that error is less than 10, meaning that this is kind of a stable behavior, and this will be that our reward is from in this range from 10 to 100. 100 is the ideal case when we don't have any errors, and we have also this penalization term when we have our agent is crashing our drone in a simulation mode. We are penalizing and giving this minus 50 reward. And if and we are also giving some survival bonus if during that learning process our agent will stay alive for let's say 2,000 time step, or will end our will solve the process. In this case, solving the goal is then keeping that UAV in that position within accepted range of oscillation. Let's say 3,000 or 10,000 steps. Then in that case, we'll give this plus 2,000 positive reward. So this is the technical details about the algorithms that we have used. So this is actor critic method. So here agent here is actually we have these two neural networks. So for this one for taking the action or learning the parameters of the policy. The policy is the mapping function for each state. We are taking how we are taking each action from this state. Let's say our policy is normal distribution. Then in this neural network should learn that that parameters of that normal distribution, the mu and sigma, and based on that it is taking that action. And also, but that action is also the input for this second neural network. So this is the input here is the state information, that the action, this current action. So it is trying to evaluate how good or how bad is this action, and then that action will be sent to the environment. Then it will return. It will send back this reward information. And so this approach, this actor-critic approach, has its drawbacks. So that's why some of the authors introduced this deep deterministic policy gradient method, which is the main difference is that we have the replay buffer, meaning that we are keeping all of the previous we are keeping the history, and then kind of combining that supervised learning logic here. And also they are using this target networks. And this twin delayed DDPG or TD3 algorithm is the extension of the DDPG. So this is one of the state of the art deep reinforcement learning algorithm. So this is twin. Instead of having one critique, it has this two critique network to address this. There is this problem overestimation problem. We have one actor, and this is that target network. After some time, so the algorithm is copying that learned weight into this target network, and it is using this target network for data generation. And during that data generation, it is learning the new weights. After some, let's say, 1,000 time step, or and there is another option for smoothly transferring this newly learned weight to this target network. So this is that TD3 algorithm. So there are lots of technical details which I am skipping here. And our experimental setup was this one. So this is a simulation. We have this in our RLDroneSim platform. We have this. This is our simulation platform. One task that we have implemented is solve this stabilization problem. And we have our evaluation metrics where we are tracking this error, accumulated error between this vertical direction and this horizontal direction, and this stability duration. Sometimes we are also keeping that track on this crash rate, how many times our agents are crashing. So the future work and acknowledgement part. So this project was implemented in this within the support of this Afeyan research grant. Here are our project team, and in the future we are trying to extend the capabilities of this platform by introducing new physics engine. There is another very well-known physics engine, NVIDIA Isaac, but that in the integration part with that gymnasium environment, it is not as easy as which was with the Gazebo. But later we'll also include this one, and we'll continuously extend the capability. We are planning to extend the capabilities of our platform, and all of you are welcome to download the codes from here, and this is the documentation, and help us to extend this this platform. So thank you. If you have questions, please. Thanks.
Any questions?
Hello, thank you for presentation. I wonder what are your estimations how it will behave in offline adaptive training phase, because the work, as much as I understood, all was done in simulating environment, right? So in real world, you may have such factors like wind and etc. How it is going to affect the policy.
This is that sim to real gap, and in simulation mode we have some good learned model, but actually they are not good enough that we'll try them in the real environments. We are waiting that actually our experiments are continuing. If at some point we'll have very good trained reinforcement learning agent, meaning that TD3, the weights of this TD3, so all of those are, so this is the neural network, this is all of, and these are the neural networks. If at some point we'll have that very well trained reinforcement learning agent, it will give us the hope that our drone will not crash, and then we'll try it. And actually, we were planning to do before this talk, but at this moment, there is very high chances that our drone will be crashed. But in the near future, this is actually in the future works session as well. Then in the future, the final part will be a final part of this project will be when we'll try it in the real world, because no one cares about that good result in the simulation mode. So I hope in the next within the next two months we'll have that good results, and maybe we also will share. We have your contacts, and we'll share update with you.
How you evaluate the performance, to achieve the highest possible cumulative reward, doing less actions? How you evaluate?
Evaluation. So the evaluation here is that when we are switching on that graphical user mode and looking that it behaves well or not, it is crashing or not, or does it have this oscillation or not. When we are applying that trained reinforcement learning agents. But also we have this tracking errors. So we are also calculating or keeping track of all of these errors. And if we have one, let's say we can compare it with that ArduPilot is providing that some default values of that KP, Ki, and KD, and we are comparing with that result. And at this moment, that default values are much better than our agents output. But we are sure that at some point we'll beat them.
Thank you.
It's on. Thank you for the talk. My question is regarding the loss for reinforcement learning. Can we jump back to the loss? The loss that consisted of 3 terms.
This one or which?
Oh, yes, this one. Here we penalize error oscillations, and penalize large control effort. But we do not penalize integral of error. So it means it doesn't matter then that there is a constant shift in error.
So this was just an example how the reward function can look like. So this is this is not the actual one that we have used in our training process. So I just showed during the talk that this can be one version of the reward. So this is not the actual one that we are used for training. And actually, this is not in the terms of the reinforcement learning. This is that reward function which we want to maximize over our action. So our actual reward function at this moment is
sum of rewards over time.
So here the reward is this one. So we have our base reward. This is 100. And as we have this error terms, these nine error terms, we are normalizing them into this from this 0 to 10 to the 10 interval. And 10 means that our agent crashes, or from that error from that in that error term, we have our agent is performing very badly. And in this case, if across all of that nine dimension, we have that 10. The value of our reward will be 10, which is the worst possible case here. And also it can be the worst one will be if we'll also penalize by this minus 50. But our reward function is this one. From 100, we are subtracting these error terms. and this error terms is actually containing all of that relevant information. If our agent will minimize this error, meaning that if it will learn to get this 100 for each time step, meaning that it has learned the way to minimize this error, or making them zero in that case.
Okay. Okay. The second question is about linearity of PID controller. PID controller is linear, and it puts out the input that we apply to the actual controller. It can be a servo motor or something else. But the thing is that in practice, everything is limited. There is no linear systems in practice. They're actually non-linear, and controls are limited. We cannot actuate infinitely large because we have surfaces that are somehow limited. We have voltages that are limited. How is it applied in your model? Can we imply some limits for your model so that it can behave in real world?
All of that physical constraint will be is implemented in that ArduPilot autopilot, because that we are not touching that actual autopilot because it is designed by the huge community and it is working. We are just in this case we are adjusting that PID coefficient. If this is that ArduPilot autopilot is working well in general in practice, almost in all of that UAVs they are using that ArduPilot's autopilots, then we are just playing with its coefficient. We are trying to make it much better. But that physical limitations, I think it was taken into account in that actual autopilots, how that autopilot is working.
Okay.
So we are operating in this high level.
Okay. And the last one is where is it actual PID controller? What does it control? So inside this.
The actual PID controller controls that is generating that actual, let's say that voltages, which will later send to the motors of that let's say quadcopter or any other UAV. The actual PID controller is responsible for this one, and there are this KP, KI, and KD these gains. But we can start apply reinforcement learning and try to learn that actions which for this motor, let's apply this voltage in this for this motor, let's apply this voltage. But this problem can be solved from that classical control theory, and this is solved for this problem. And we are actually abstracting from this level, and we are playing just with this coefficient, these gains. But the actual controller is the one who is responsible for sending that control signal to. There are other components which is getting that voltage and sending it to that motors, and they are and then it will be converted to that at which RPM that specific motor should turn.
Okay. And so in your RLDroneSim, what actual vehicle we control? Is it quadrotor or?
So here we have that quadrotor, but we can change it to the hexacopter, and we are trying also to implement also that for the fixed wing drones, because the dynamics are very different for that quadcopters, the copters, and that fixed wing drones. In the later future tasks, we'll implement also this one. This is very interesting for us.
Thank you. You said that currently in the simulator there are PI and D values, default PI and D values, which are better than the ones that you're able to learn. So how are these default values calculated? Are they just like hand-tuned? What's
ArduPilot is when you are inserting so you're inserting the model of your UAV, and there are some default values that you can choose, and there is an option. I forgot to mention this part as well. There is also option to do the auto tune, meaning that you are running your real UAV in the real environment. Let's say takeoff in the 50 meter or 100 meter. You are pressing that button auto tune, and it is trying to tune its gains based on that condition. And actually, during this within this project, we have purchased two different UAVs. And we were trying to do that auto tune, and in the 50 meters. But every time it failed to do that auto tune because it said that there is very windy, there are lots of oscillation. It asks to have that idealized environment, but actually we were doing that auto tune later to respond this kind of the windy weathers. So actually we have tried this 10 or 15 times for the different UAVs, and every time we have failed, and the reason was that there are lots of oscillation. So that was the first motivation to have this project AutoTune, RL4 AutoTune. The first version of the project was this one, RL4 AutoTune.
And do we know what they use internally to do that auto-tune?
Actually, okay. No. Maybe there is some logic. It is trying. Maybe it is trying some this manual, not manual. It is changing. It is changing that coefficient and trying to see the response. But if maybe it will change that coefficient, and if it is very windy weather, then maybe the drone will be crashed. So that's why it is preventing it and saying that I can't do that. I can do this auto-tune part.
Thank you.
Thank you.